This is the first example that we will see involving a titration situation. So we are told an IV line was ordered to titrate between 2 and 3 micrograms per kilogram per minute. We are to increase the dose by 0.1 micrograms per kilogram per minute until the patient's systolic blood pressure stabilizes below 120 millimeters of mercury. We're also given some information about the patient, weighs 90 pounds, and the IV solution that we will be using. The first thing that we want to do is to find the initial rate to set the IV pump. And we're going to put all this information in the chart. So before we jump into this, just to recall, we know with titration, as we had read and we watched some videos, a patient's going to be ordered to receive a beginning amount. And in this problem, we're actually not told to start at anything in particular. So what that means is we're going to assume we start at the minimum dose of 2 micrograms per kilogram per minute. And depending on whether or not the patient is responding the way we think he or she should, we're going to adjust the medication. So in this problem, the patient needs to, and we're looking for, their blood pressure to stabilize below a particular amount, the systolic blood pressure, that is. So if the blood pressure does not stabilize after this initial dose, what we need to do is to continually increase that dose by 0.1 micrograms per kilogram per minute. So what this requires us to do is to make multiple calculations. We're going to start with an initial dose, which, very much like a critical care situation, will require an initial milliliter per hour rate. But then whether or not the patient responds positively, that's going to dictate if we need to increase the dose. And if it does increase the dose, we might have to continually calculate a new rate because the dose is going to increase. So what I'm going to do, and that's why we have a chart here. We have a chart here so we can organize all this information. I'm going to go ahead and fill out the first line. The time, I just made this up, it's 0900. The dose, the initial dose that the patient is set to receive, we are not told start at such and such, which means we should assume we'll start at the minimum value. The minimum dose that a patient would receive would be 2 micrograms per kilogram per minute. And what we need to do is to figure out what rate in milliliters per hour should we set the pump to. So this is very much like a critical care situation that we saw in some previous videos in this modules. So what I'm going to do is I'm going to convert micrograms per kilogram per minute into milliliters per hour. In order to do that, as we saw with critical care, I need to multiply by the patient's weight. So I'll start by writing my dose, 2 micrograms per kilogram per minute, and I need to multiply by the patient's weight in kilograms. And if I do that, then I'll know the total number of micrograms per minute. Up above, I'm told the patient weighs 90 pounds. So I'm going to bring that to the side, and I know 90 pounds. I'm going to divide by 2.2 because there are 2.2 pounds in 1 kilogram. And I know with weights, especially weights over 10 kilograms, I'm going to round to the tenths place. So if I take 90, I divide by 2.2, I get approximately, rounded to the tenths place, 40.9. 40.9 kilograms. So that's the patient's weight in kilograms. Now I'm going to, as soon as we multiply by that factor there, kilograms will cancel. I want to convert micrograms into milligrams, because I need to use the dosage strength of the bag, and the bag is 80 milligrams for 200 milliliters. So in order to get to milliliters, I'll first convert my micrograms into milligrams. All of this is a bit of a review, so if you think I'm going a little too fast, you might need to go back and review some of the videos that we saw maybe with the critical care and the dosage by weight. So by multiplying by 1 over 1,000, that'll convert into milligrams. Finally, milligrams into milliliters. All of this is a review of the critical care problems that we saw. So I circled milligrams, but I shouldn't have, because milligrams is going to be going to milliliters. That's what I want. And now finally, we'll go 60 minutes into 1 hour. Minutes will cancel, be converted into hours. So what I'm going to do is multiply all of the numerators, very much like I did in the critical care example. So 2 times 40.9 times 200 times 60 gives me 981,600. And if I multiply all of the denominators, 1 times 1,000 times 80 times 1 gives me 80,000. Now when I put that quotient into my calculator, I will get exactly 12.27. I need this exact value, right? That's the exact value. It's going to be very important that I get the exact value. But knowing that information, that's great. That's the exact value of this division problem. But what am I going to set the pump for? The pump needs to be set to the tenths place. So to set the pump, I will set the pump to 12.3 milliliters per hour. Now, let's just think back what we did. We were told the minimum dose was 2 micrograms per kilogram per minute. I did the work to convert that to milliliters per hour. In order to start this titration dose, I would start the pump for 12.3 milliliters per hour. In the next few examples, what's going to happen is we're going to need to adjust this rate because, as we'll see, the patient is not going to respond positively to this. So we're still not stabilized, so what we need to do is to adjust. So let's look at the next slide. So now we need to recall the order we just completed. We're titrating between 2 and 3 micrograms per kilogram per minute, and we're to increase the dose by 0.1 micrograms per kilogram per minute until the patient stabilizes. We are told here we are to assume that the patient's systolic blood pressure did not stabilize after that initial dose. So what we need to do is to make an adjustment. What is that adjustment? Well, according to this problem, we need to increase the dose by 0.1 micrograms per kilogram per minute. So if I were to add 0.1 micrograms per kilogram per minute, I would have 2.1 micrograms per kilogram per minute. So that's great. The dose increased by 0.1 micrograms per kilogram per minute. Now what I need to do is to go and reset the pump. So what's that going to mean? That means I need to redo my dimensional analysis. So what I'm going to do is pause the video, and I'm going to redo the dimensional analysis, but not with 2 micrograms per kilogram per minute, but with 2.1. So I went ahead and started with my dose of 2.1 micrograms per kilogram per minute, and I followed the same steps. I multiplied by the patient's weight, I converted micrograms into milligrams, then used the strength of the bag to go into milliliters, and finally converted minutes into hours. I multiplied all the numerators and denominators to find that the patient needs to or should be receiving 12.8835, and I'm writing the exact value of what I got when I did that division problem, and you really should get in the habit of doing that. Let's write the exact value and now round, right? What are we going to set the pump for? I'm going to set the pump for 12.9 milliliters per hour. And the reason I'm doing 12.9 is because we're going to the tenths place. Most pumps are going to be precise to the nearest tenth of a milliliter. So, what did we see right then in this problem? We had to come back and see that the patient did not stabilize, and a half hour later, from 0900 to 0930, the patient needed to be given an increase of the dose. So we had to redo all of that calculation that we saw previously. We're multiplying by the weight, going into the different metric units, and using the bag. We did that exact same thing to figure out what the rate is. So let's look at the next slide. So now we're told that we're supposed to assume that the patient's systolic blood pressure still did not stabilize after the initial dose. So we need to make the appropriate adjustment and determine the new rate to set the pump. Okay, this is getting a little bit of annoying, right? We're doing the same calculations over and over again. Of course, we want the patient to stabilize. That's the goal of the situation. But with titration, we aren't always guaranteed that that's going to happen. So what we need to do is to continually adjust the dose. So what I'm going to do right now is to once again adjust the dose by adding another 0.1 micrograms per kilogram per minute. I'm going to add 0.1 to get 2.2 micrograms per kilogram per minute. So I'm not going to spend too much time on this. You should know what to do. Go ahead and pause I'm going to pause the video. If you want to pause it and try it, I'm going to do all the dimensional analysis once again to get milliliters per hour. So I went ahead, did the same calculation that we did on the previous 2 pages there, and I got 13.497 as my exact value, and then I rounded that to the 10th place to get 13.5. Now, as you might be able to tell, this could get a little bit tedious if we have to do this calculation over and over again. Thankfully, there is a better way, and we can summarize all this information by considering the relationship between the dose and the rate. So let's go to the next slide and summarize this relationship. So I've gone ahead and placed the dose and rates in this summary table where we can see when we had a dose of 2 micrograms per kilogram per minute, the exact value in milliliters per hour, not the pump, but what we needed to do exactly was 12.27 milliliters per hour. When we increased to 2.1, we have the accompanying value here, 12.8835 milliliters per hour. And with that last dose of 2.2, we got 13.497. Thankfully, there is a relationship between the dose and the rate where we don't have to continually do all this dimensional analysis over and over and over again. What we can do is to consider the relationship because there is a direct relationship. There is a direct variation between these quantities. There is a direct variation between the dose and the rate. So what does that mean? If you recall from last week, we can consider the ratio of the dose over the rate. And if there's a direct variation, we know that this ratio will always reduce to the same constant of variation. So let's look at this ratio. Let's look at the ratio of each one of these. So if I take the dose of 2 and divide it by 12.27, and I compare that to the dose of 2.1 and divide that by 12.8835. So let's look at these, that should be a 5, and then look at 2.2 and divide by 3.497. Let's look at these ratios. When I put 2 divided by 12.27 in my calculator, I get approximately 0.16. When I put 2.1 divided by 12.8835 into the calculator, I get approximately, once again, 0.16. This is a good sign. So now that last ratio, 2.2 divided by 13.497, once again, I get approximately 0.16. This is a good sign. This is telling me there is a direct, this is confirming, I'm saying that there's a direct variation, and this is confirming that we are seeing the same constant of variation between these two. That should make sense. When we started with the dose and we were multiplying by all those conversion factors, we were getting the rate. Those conversion factors didn't change. So we were multiplying by that same multiplicative factor to get the rate. What does this mean for this problem? How does this relationship help us with this calculation? Well, if the dose over the rate gives us the same constant of variation here, then what we know is we can rearrange this. The dose can be found by multiplying the rate times this constant of variation. And this is a formula that students in Mat 150 need to memorize. For titration problems, and actually for all dosage problems, the dose and rate vary directly. We can write and generalize that relationship with this formula. So what can I do? What I need to do is to find this constant of variation. That's exactly what I did up above. I found that variation constant, which we also call a factor number. So when you're asked to find a factor number, you're looking for that variation constant. It's the same thing. And we found that up above. We found that when we plugged in one instance of the dose and the rate, we found that that constant, K, was approximately 0.16. This constant of variation, for future problems, you will always round to the hundredths. When you're finding the constant of variation, then you need to round to the hundredths place. So the formula, the equation describing this situation, the dose is related to the rate by this formula. The dose is equal to 0.16 times the rate. And now we can use this formula to answer questions. We don't have to constantly be using dimensional analysis. So if the dose changes, which we see here down at this final problem, we're going to suppose the patient has still not stabilized. So what we need to do is to, instead of doing dimensional analysis, use this equation to find the new rate. What do we need to set the pump for? Well, if the patient has still not stabilized, we need to once again increase by 0.1 micrograms per kilogram per minute. So that means the new dose is 2.3 micrograms per kilogram per minute. So what we need to do is to determine if D is equal to 2.3, if the dose is equal to 2.3, what is R? What is the rate? So we know the formula relating these two variables. The dose is 2.3, so I'll plug that in for D. And now if I just divide both sides by 0.16, then I will have the rate. So if I plug in 2.3 divided by 0.16, I get exactly 14.375. But what we're going to do, obviously, if this is a rate, we're going to round this to the tenths place. So 14.4 milliliters per hour. 14.4 milliliters per hour. Now, if you were to go and do the dimensional analysis, you might find you get a slightly different answer. And the reason is because we are rounding, right? When we are rounding, we're finding the constant of variation, the factor number, we're rounding to the hundredths place. We might have a little bit of a rounding error, and that's okay. That's one of the prices, the costs of having more of a shortcut to finding the relationship here. We could find the exact value. By looking at the exact ratio instead of rounding, we could go out more decimal places to get a little bit more of an accurate answer. But overall, with titration, what we're going to be seeing is that we're often going to be first converting an initial dose into a rate. That's going to be very common. The patient needs to be given a dose, needs to be converted into a rate. Great. Now, instead of constantly using dimensional analysis, what we're going to be doing is using that dose and rate, knowing there's a direct variation between those two variables. We will then use those two quantities to find the factor number, find the constant of variation relating those two, and then use that equation to address problems. So now that ends this video, which has been a rather long video, and we're going to move on to more examples in other videos.